Welcome, everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. Today, we will finish these last few slides for cloud storage, and then we'll move on to the next part, which is distributed file systems and the Hadoop distributed file system. But before we start, I will ask a few questions to make sure that you're following, and then we'll continue. So my first question to you is, which one of these cannot be stored as an object in S3? The first episode of Star Trek Discovery, or the 300 petabyte dataset containing proton collision released by CERN, or the static pages of a website, or an archive backup of my 2 terabytes hard disk. As a single object. And indeed, 300 terabytes in a petabyte in a single object doesn't fit. What is the limit in S3? Anybody remembers? It's in terabytes, yes. How many? Hundreds, less than that. It fits on one machine, yes? Five, yes, exactly, 5. My German and my English got mixed. Yes, 5 terabytes, absolutely. And the 300 petabyte data set is, of course, more than that. We would, of course, be able to store it, but it would have to be in plenty of smaller objects, of course. All right. So this was the first one. Then, what is the best practice? I showed you how you can scale out, scale up, and write better code. In which order should you normally try this? As a general rule. Yes, you remembered well, indeed. The first thing you should do is try to write better code. Try to use less space, to have more efficient data structures, to have a more efficient memory footprint. Then you can try to duplicate the machines, buy more and more and more machines in a data center. If it still doesn't work, you can, of course, scale up the machines. It's just a general rule, of course. There's always, on a case-by-case basis, you could always justify, for example, some people nowadays also sometimes scale up a little bit before they scale out, which can have advantages too. All right, but I gave you between scale out and scale up the economic reasons because of the economies of scales that we can do. All right. Do I have another one? Yes. Do you remember what there is in a data center? And yes, plenty of small chip machines. Absolutely. This is in order to scale out, as we discussed. All right. And I have another question for you, but this one is about today. So of course you don't know, but you can try to guess. We will see in HDFS that we will now attempt to, in order to increase the size of the file that we can store, we are going to cut them into blocks, and we are going to read one block at a time. So what do you think is the size of these blocks? As a reference, on these laptops that you have right here, the blocks that are used by your laptop are a few kilobytes, a few thousands of bytes on your local laptop. But here we are talking about a data center, tens of thousands of machines spreading blocks over the machines. So according to your intuition, what would that be? Is it the same as on a local system? Because in the end, it's all stored on a disk. Or is it 128 megabytes roughly? It's orders of magnitudes, which is a good compromise between latency and throughput. Or is it 2 terabytes because you try to have one block per machine, basically, and 2 terabytes fits on a lot of local disks nowadays? Or 512 petabytes because we're in big data. And the majority is correct. And why? We will see in the HDFS lecture. All right, so that brings us back to where we were last time. All right. So I left you with the REST API. The REST API, you have to associate this with the web, with HTTP. When you type an address in your browser, and then a web page comes back. This was designed as a human-to-machine interface in the sense that the server is always available, and you as a human type an address in your browser and get the page. But now machines talk to machines. And so it's not unusual that it's the machines that send an HTTP request over the internet and then get back some useful information. And of course, what you will send is no longer an HTML page or pictures. Instead, it's going to be data, right? Or codes or machine, something that machines understand, right? And this is what we call REST. And REST is based on the same protocol as what happens in your browsers. But again, it's just for programming stuff. And I told you that the way it works is that every request contains a verb called a method and a resource. These verbs, there's a few of them, but I'm going to just focus on 4 of them: get, put, delete, post. So one of these verbs together with a resource. This resource is going to be given as what we call a universal resource identifier, URI. And so you have the method plus the URI that constitute a request. And then, of course, together with the method and the URI, you can also ship some data. That's called the payload, right? And so it looks like this when you actually communicate. And that's the same on your browser. Every time you type the address of a website, this is what's happening behind the scenes. Your browser is sending a request. Very often it's going to be a GET, but sometimes a POST. Together with the URI, that's what you type in your browser address bar, basically the URI. But then there's going to be plenty more with the images and that are linked from the page and some more content. Then the body, that's especially when you post or when you put, I will say, I will explain. And then the response is what you get back. So first, a status code. You know the 404. If it's not found, the status code is 404. That's the one everybody knows. But there's plenty of other status codes. And then, of course, some header with metadata information, like the type of content that is returned. And then the body, which in the case of your browser is an HTML page or some images. But in the case of computers and REST, that can also be XML, JSON, CSV, text, any kind of content. And we'll study all of that in this semester. So let's get into the 4 of them. Oh, by the way, I don't want to scare you, but this is an example. If you would see what your browser is doing, you can actually see it in the developer's view if you activate it, but that's the sort of things that happen. And fortunately, we have a browser that is going to display it nicely for us without us having to bother with this. So get is the simplest method ever. It's just to get a resource. So if you send a get with some URL, URI that contains the address of a web page, then you get back the web page. If you send the URI of an image, then you get back the image. Of course, then it's probably going to be some binary data in the body, right? And we say it's side effect free because you do not modify anything. You're just requesting some data, and that's it. You're not actually modifying anything. Then we have put. Put is something that typically humans are not using with their browser. It's more machines that do that. It's when you want to write to somewhere, assuming you have write access, of course. It's going to, imagine you have some data and you want to put it somewhere so that other people can get it with a get. So when you do a put, you say the URI that you want to put that data on, and then you send over the actual data together with your put request. What happens is that if later somebody else or yourself uses a get on the same URI that you use for put, then you get back the data that you sent, right? A bit oversimplifying, but that's the idea. So put get is a little bit like writing and reading, right? So this is very useful if you use a REST API in the context of a database, because if you create some new data and want to put it somewhere, then you can, right? Then you can delete the data at a specific URI. Then what happens after a delete is that a get is going to be returning what status code? 404, right? Not found, if you've done a delete. But again, put and delete is not something you do in your browser every day, right? Typically in the browser, it's going to be mostly get. But there is one that your browser can also do when you fill forms. If you fill forms and then you click on submit, then it's going to post it. It's going to typically be a post request that ships over the contents of the form that you've just filled, right? Post is one of the most generic methods that there is. It's pretty much to do everything else for which get, put, delete do not make sense, right? So it's very popular. It's also useful when you want to create data but you don't know where yet, right? So for example, you don't have yet the ID or some identification for the data you're going to put. So you cannot use put, because put would require you knowing the URI. So instead, you just post it to some generic URI, and then it will answer back telling you to what address it was actually stored. And then you can use a get together with what you get back from the post, for example. Okay, who is following? Right? Okay, so we are not asking you to write any such interfaces or to use them. You just have to know that this is an extremely simple interface between machines and machines. Get, put, delete, and post. The whole web is based on that. And it's a very common practice that when you have a system like S3, like Azure Blob Storage, but also HDFS, and so on, and so on, and so on, that they also offer an interface like this that is based on a REST API. And then when you write libraries in many languages like C, C++, Java, R, Python, and so on, what people commonly do is that they actually put that as a wrapper around the REST API, right? So it's much simpler to implement than access from many programming languages, because any programming language understands HTTP. There's always an HTTP library in programming languages. And in the very case of S3, as an example, then we can use put, delete, get on objects and buckets. So if you get an object, then you basically get back the content of the object at that URI. If you delete an object, then it's gone. If you put an object at a specific place, that just stores it, and then you can use get to get it. For a bucket, you can also create a bucket. You can delete a bucket, and you can get, what is it to get a bucket? You list what is in the bucket, right? It gives you the contents of the bucket, and then you can navigate in there. All right, so this is the REST API, okay? So again, I'm not giving you more details than that. Just know that it exists, and this is one of the ways to communicate with S3. Many data scientists, in fact, will not bother with this API. They will just open their browser, go to the S3 website, click on upload, and then upload the files directly through the browser, right? Which is the user interface, the user-friendly way. But behind the scenes, this is what happens. Okay, that's for REST, the REST API. Now, I'd like to answer a question: is S3 a file system? What is a file system? Well, it's typically something that has a directory structure. It has a whole tree of directories with the files at the leaves of the tree. And you can navigate these or by the means of paths, right? So here you have a directory called food. Then inside you have 3 fruit and vegetables. Inside fruits you have orange and strawberry and so on, right? So there's the notion of a hierarchy of directories and files. In S3, there is no such hierarchy. As I told you, you just need a bucket ID and an object ID to identify an object, and that's it. That's all you need. However, there is a trick to emulate or simulate a hierarchy. It's to put slashes in the object IDs. So you could create objects with slashes like this. But what's important to understand is that S3 treats the slash as like any other letter, any other character. So it's all flat to Amazon S3, right? All of that. However, for convenience, when you go to a browser and go to the S3 administration console and want to see the data in there, these slashes are going to be nicely interpreted in a directory structure, but you have to be aware that it's artificial, right? They do not, this structure does not actually exist. It's only that the interface in your browser, to be nice to you and friendly to you, is kindly interpreting the slashes in such a way. Okay? For whom does that make sense? Right? So it can be convenient. So you can still have the impression of having some directory structure to organize your data. A very popular way of using S3 is to store static websites. It's the cheapest way, I think, today to store a website. S3, or of course, the equivalent for Azure and Google. What do I mean with a static website? I mean a website that doesn't interact with you. You just go on it and you see a page and pictures, and that's it. There's no interaction. A counterexample of a static website would be a web shop where you actually browse for products and then the pages are dynamically generated with your products, right? Google is not static. If you Google something, it's dynamically generating the results, right? But a static page is just displaying the same thing to everybody. And using a cloud storage service is automatically binding that to some URI that you can go to, and you can even bind it to your own domain if you buy a domain and bind it to it. And then what's really nice is that it's super fast because S3 is designed to be very efficient, and it is very cheap in terms of hosting. So for example, the JSONic website that you're learning throughout the semester, the language, this is using S3, right? And it just displays the same static pages to everybody that goes on it. Okay. The button here, live, the live trial is of course not part of the website. It's just redirecting to somewhere else because that part would be interactive. Okay. Now, another way to use S3, so I gave you a few use cases like Netflix, like if you want to stream series and movies, then you could store chunks of the series and movies as objects in S3 and then get them on the fly when the users watch. They just download from S3 all the small chunks of series that they are watching. But you can also store data sets, and that's actually what we are interested in this lecture. Right? So a data set typically is going to be stored as plenty of objects in there. I have some directory. So again, that's all emulated with the slashes. That's as I explained here, that this is all just nicely displayed. But basically, we have these objects here that are part of a data set. What we say is that this data set has been sharded. Because if you look at what's going on in here, there are several things that might jump to your attention. First, the file names don't make much sense. It's just a bunch of letters that increase alphabetically. Sounds very artificial, right? And then you see the size is almost always the same one, right? It's roughly 500 megabytes. And what happens is that that data set might have been, I don't know, 100 terabytes in size, but it's very, first, it doesn't fit in an object, so you cannot upload 100 terabytes as a single object, so you need to cut it into smaller pieces. And then there are automated ways of doing that. When you have such a file on your hard drive that might be very big, well, 100 terabytes you won't have, but let's say 10 or 20 terabytes on a big hard drive. You can use command line utilities that automatically cuts the file into pieces, right? Cutting at the end of a line to basically preserve the lines. And this kind of command line utilities are going to generate that sorts of file names, right? XAA, XAB, XAC, XAZ, they just increment the letters, right? And that cuts it into small chunks. And then you notice when you have this kind of chunks, it's much more convenient to upload it to S3 because you basically click on upload, then you select them. And then maybe it's going to do a few parallel at the same time, maybe 5 at the same time, and then it keeps uploading a new one. Why do I say it's more convenient? Because once in a while, it fails. And if you try to upload one very big object, the risk is much higher that it's going to fail. And of course, because of Murphy's law, it's going to fail exactly at the end when you're about to be finished. And then you have to start it all over again, right? So to whom it happens, this sort of thing, you try to upload something, then it just fails. Big files. Some of you, right? And so the trick is to just divide it into smaller pieces. And what happens is that maybe you upload 100 of these, maybe 98 are going to fail, but that's okay. 98 will succeed and 2 will fail. Then the 2 that fail, you try again, but you only need to re-upload those that fail, which is much less. So it's for practical reasons, very convenient to cut the data sets in chunks in this way. All right, who is with me? Right, okay. And by the way, you don't need any programming for that. You can really go to the website, to the console, the administrative console of your account, go to S3, and it's all in the UI. You click buttons, you say upload, and just upload from your hard drive to S3. Okay. S3 is also used for backups, and there's a price model that is based on the idea that if you just want a backup and you don't care if getting the data is fast, so for a website like this, you obviously want it to be fast so that people get the page immediately. But if it's for a backup and you just want to keep it in the long term, then you don't care if you get your data in 1 second. You don't mind waiting for a few hours or even 24 hours before getting your data. And if you accept that it would take a lot of time to get the data, then the price is much cheaper, even cheaper. And so this is how the price model is working, right? So Glacier is basically the idea that you pay much less, but you accept that it might take a few hours to get back your data. Okay, and then you have things in between that might provide a bit less availability, even cheaper, but maybe you have to pay every time you want to get an object, right? So it's just a matter of cost model. That's for the people who access it infrequently. All right. And so a final word on S3, it's the idea that when we have storage in this way worldwide, you want to diversify geographically and replicate your data at multiple locations. For example, in America, in Europe, in Asia, and so on, right? So one of the reasons is, of course, to be resilient to natural catastrophes. If there is an earthquake somewhere or an entire data center burns down, which does happen, you see it in the news from time to time, then you do want your data to be replicated at multiple places, right? It reduces the risk that you lose it. So resilience to natural catastrophes. And the other point that is not to be neglected is the lower latency. If you have a company that has people who access your websites all over the world, then having a copy of your data at multiple places is going to make it faster. Because imagine that all of your data would be in Europe, and somebody connects from Australia. That's going to take a bit more time to get to the data, because the browser is basically communicating back and forth, but every time it's back and forth, it needs, there's a speed of light in between, right? So you are limited by the speed of light and all the length of the wires, and even the wires that cross the ocean, right? But if you have your copy of your data at multiple places, then whenever a user in the world connects to get your data, they will just connect to the nearest location, then it's going to be faster. Who is with me on these 2 points, right? So this is the benefits of having a cloud and being replicated at multiple places. Now I have very, very few slides, very few slides on Amazon Blob Storage, which is kind of the equivalent of S3. That's the storage service of Azure, right? Why am I showing you this? Because we have more information about the way that this one is implemented. S3, it's a bit of a black box. We don't really know how it's done. There is no information. There is no publication that tells us how it's been done. But Azure Blob Storage, there is a paper that you will find in the Moodle. And so since you know S3, it's actually not so complicated to learn Azure. If we compare, for example, in S3, to get an object, you need a bucket and an object ID. But in Azure, you just have something different. You need an account, what they call a container, the equivalent of a bucket, and then a blob, which means binary large object. So it's an object, basically. So you need 3 components to identify an object ID instead of 2. But again, that's just a small detail. Now in the API, the kind of objects that you have, Azure Blob Storage is slightly more complex than S3. You have several kinds of objects. You have block, append, and page objects or blobs. Blocks, we will see, are actually going in the direction of the distributed file system that we'll see in the next lecture. So it's kind of a hybrid form. Append and page, don't worry too much about them. It's for virtual machines, for example, for the memory of virtual machines that you have the page blobs. It's smaller chunks of data that support the virtual machines. And append is for the logs. When you want to log data and you only append at the end, then it's very convenient to, it's very efficient to have an append blob. All right, and the limits now you see are a bit higher on Azure. So S3 has 5 terabytes. On Azure, with block blobs, you can have 190 terabytes for a blob. Append, it's 195 gigabytes, a bit smaller, and 8 terabytes for the page blobs, right? And one of the reasons why we are able to scale, for example, for the blocks to 190 terabytes is precisely because we cut the data into blocks. Right, but that I'll explain in HDFS. All right, and the way that they document, the way that it works in Azure is that they have these data center rooms with all these towers of machines, right, with all the machines that are piled up on top of each other in these towers that we call racks. And typically, they will have maybe 10 to 20 racks in a room. Every rack has 18 machines with a lot of drives in them. And if you do the multiplication with all the drives that you have in there, it's roughly 30 petabytes in one room, in one data center room. And they call that a storage stamp. And they have these kind of storage stamps all over the world, maybe even several of them in the same data center. And they try to keep them at 80% capacity, meaning that as soon as it's more than 80% filled, the data in there, they try to move it somewhere else. That's exactly the same idea to try to avoid having your disk full, right? Whoever has had the disk full and got a message, right? It's very annoying, right? And it tells you cannot have the disk completely full. And here it's the same idea. They keep it at 80%, and as soon as it's more than that, they just reorganize and move the data somewhere else to always keep it below 80%. Okay? And the idea is that these stamps are synchronized. So this is basically one stamp and one stamp. Don't worry about the details. But the data is replicated across the storage stamps. That's exactly what I explained here. The idea that you want to replicate the data at multiple places all over the world. So we replicate the data between the storage stamps. And we might also replicate it within a stamp several times. What do I mean with synchronous, asynchronous is that when you upload data and it replicates it within the same stamp, so in the same room, it's keeping you waiting. This is what synchronous means. You have to wait until it's been replicated within the same room. But for the replication to other places in the world, it's not keeping you waiting. It's just telling you, that's it. I already have enough copies right here. And after you're gone, in the background, it's going to ship it over to some further places elsewhere in the world. Okay? That was my last slide. I told you not so, I just had these 3 slides on the Azure Blob Storage. You can read the paper if you're interested. Yes, we have a question, maybe the microphone. That the people on Zoom can and hear you.
About the maximum storage capacity on the last slide, was it like trial and error, or is there an actual theory that aims to optimize the fact that it's at 70 or 80% that it's optimal? Or is it just like an arbitrary value that they're taking just to be sure?
I think there was probably a bit of trial and error. It's probably also the same kind of things that you aim for your laptop, right? I mean, for my laptop, I also have this number in mind for practical reasons. But I think it's not based on a theory. I just think you have to try and see which works. And then at some point, it's sufficiently fine-tuned that it works, right? And these kind of parameters, by the way, they give it in an academic paper. So for example, they say we have 20 racks, we have this and this many nodes and so on. This evolves over time because the hardware evolves, the size of the disk evolves and so on. And so it might have changed in between. It might be now more than 30 petabytes if they have bigger disks. And also, I could imagine that because of the different numbers in hardware, that number might right here, 80%, might also drift a little bit. Could go down, could go up. I think it's really, they have the people working full-time maintaining all of that, and they probably monitor it with all kinds of metrics to see that on availability, on durability and so on, so they can basically adapt the parameters to keep it running, right?
Thank you.
Thank you. That's, by the way, one of the benefits of having this as a service, because this is a service. You don't have to do it yourself. All of that is taken care of by Microsoft or Amazon in the case of S3. And for you as a user, you don't need to worry about these things. You just upload your file and get them, but you don't have to worry about the details. All right. So this is just so you know how it's actually done. But if you actually use them, then you will find that it's actually relatively easy to upload and get data from there. Okay. Any other questions? All right, then I'll move on to HDFS.